right, yeah. So thanks to the conveners for giving me the chance to speak here. And I'm going to kind of switch gears a little bit from some of the geochemistry and experiments we've seen to talking about some large-scale, long-term dynamics and planetary evolution models. So just to start off with some motivation, it's been recognized for a long time now that plate tectonics and mantle convection play a major role in planetary habitability, and that's through the influence that plate tectonics has on the long-term carbon cycle. So in particular, plate tectonics, at least on Earth, is thought to be responsible for some key components of the long-term carbon cycle. That's things like orogeny, or mountain building, which exposes fresh rocks at the surface to allow weathering to happen, and it's this weathering that represents a major sink of atmospheric CO2. And plate tectonics is also responsible for subduction, which returns carbon to the mantle, degasses carbon from the plate up through arc volcanoes, represents one of the major sources of CO2 in the atmosphere. And it's this long-term carbon cycle that's able to buffer atmospheric CO2 against variations in solar luminosity, kind of in both space and time. So in space, I mean things like the position a planet is in the habitable zone, maybe close to the inner edge or close to the outer edge. And in time, as stars go through their main sequence, the phase of their main sequence evolution. All right, so the way this works is that planets that receive, I'll go into some of the details a little later, but just for now, that planets that receive a high solar flux due to the long-term carbon cycle and the feedbacks within it will be able to maintain lower atmospheric CO2 levels. And here, planets that receive lower solar fluxes, sitting over here, will be able to maintain higher atmospheric CO2 levels. And this is in contrast to a planet shown by this dashed line that has no active carbon cycle. Its atmospheric CO2 is basically stuck at one level as solar luminosity changes. And as a result of that, this planet can only stay in a region where it has liquid water over a much shorter time scale. All right, so like I said, the fact that plate tectonics has a major role in climate has been recognized for a long time. But what's becoming thought about a little bit more recently is that climate can potentially have a major influence on plate tectonics. In particular, some ideas that have come out relatively recently indicating that high surface temperatures can potentially slow down or even stop plate tectonics altogether. So these ideas, I don't have time to go into this in detail, but from some of my previous work a couple years ago, we found that at warmer surface temperatures, plate boundaries essentially heal faster due to grain growth. This effect causes the plate boundaries to be effectively stronger and resist plate motions that can slow them down or potentially even stop plate motions altogether if you go to very high surface temperatures like Venus. There's another idea, similar but slightly different physics, coming from some work Adrian Lenardic did, where he found that high surface temperatures tend to drop convective stresses. If the stresses drop all the way below the yield stress, plate tectonics can cease. So given that there's a potential for kind of a complete coupling between plate tectonics and climate, that raised some important questions in my mind that I'm going to try to answer in this talk. And those are things like whether the initial conditions matter. Do they exert any strong control over the final steady state we reach? Are there hysteresis or divergent evolution based on initial atmospheric CO2 levels? Are there stabilizing climate feedbacks that are responsible for allowing liquid water on the surface of a planet over a broader range of solar luminosity? Are these feedbacks preserved when plate speed depends on surface temperature? And then I'm going to look at some factors that could cause a planet to lose these stabilizing climate feedbacks, in particular by looking at the effect of small land fractions. All right, so to answer these questions, I'm going to use a simple carbon cycle coupled to the plate tectonics model. It's a simple planetary evolution model. So first, starting with the carbon cycle model, it has four main reservoirs of carbon: carbon on the plate or on the seafloor, carbon in the mantle, and of course carbon in the atmosphere and ocean. So the plate reservoir, it receives carbon through weathering. So silicate weathering reacts with the rocks at the surface, washes ions into the oceans where they react to form carbonates that sit on the seafloor. And the plate reservoir loses carbon, of course, through subduction to the mantle, where a certain fraction of the subducted carbon will come out arcs. The rest of it will get recycled into the deep mantle. So the mantle reservoir, like we already kind of hinted at here, it's receiving carbon through subduction, whatever doesn't come out arcs, and it's losing its carbon through ridge degassing back to the atmosphere. And finally, of course, the atmosphere and ocean reservoirs, gaining carbon from arc volcanoes, from ridge degassing, and they're losing carbon to the plate via weathering. All right, so I'm going to go through some of the key fluxes here briefly. First is the subduction flux. The subduction flux is dependent on the amount of carbon on the plate, naturally, and the plate speed. So of course, faster plates will cause a faster flux of carbon into the mantle and up through arcs back to the atmosphere. There's the degassing flux. For ridge degassing, this is dependent on basically the concentration of carbon in the mantle. So it's a function of the size of the mantle-carbon reservoir over the volume of the mantle. This also depends on plate speed, as faster plate motions mean faster ridge spreading and a faster kind of flux of mantle into this melting zone beneath ridges. And of course, it will also depend on the depth at which melting begins, which in principle is a function of surface temperature. The next flux is probably the most important part of the model. It's the weathering flux, and this is what incorporates these stabilizing climate feedbacks I talked about at the beginning. So this is something that many authors have looked at over the years, and they've kind of developed this kind of standard form of the weathering flux. The weathering flux ends up being dependent on the partial pressure of CO2 in the atmosphere. The reason for this is the CO2 pressure in the atmosphere has a direct impact on the kinetics of the weathering reaction between carbon and silicate rocks. It also depends on the saturation vapor pressure, which is used to essentially model changes in precipitation as surface temperature changes. It's also dependent on the surface temperature itself. And this is again due to the kinetics of the weathering reaction. Weathering happens faster at warmer temperatures. And finally, it's dependent on the amount of land exposed, which I parameterize in terms of a land fraction, where the land fraction is just defined as the surface area of exposed land divided by the surface area of the Earth. All right, but there's an important caveat about this weathering function that everyone basically has used in these carbon cycle models, and that's that when you write down this kind of weathering equation, you're assuming, implicitly at least, that weathering is kinetically limited. In other words, that the reaction between CO2 and silicate rocks is a limiting step. But it turns out that at very high weathering rates, the ability to actually erode the surface and bring fresh rock up to the surface can limit the weathering rate. So that it can actually act as a cap or a maximum upper bound on how high weathering can get. And that's determined essentially by some kind of globally averaged maximum erosion rate that the planet can achieve. So when that happens, it's called supply limited weathering. And I can write out an equation for this limit, this upper bound, the supply limit, like I've done here. It's a product of a maximum erosion rate. So it's sort of an upper bound for erosion that the planet can achieve, the area of exposed land, and then the moles of reactable cations, magnesium and calcium, within this, within this land that's getting exposed and fluxed to the surface via erosion. So if you combine these two things together, the kinetically limited weathering, sort of the normal weathering, and the supply limit, you get the total weathering flux weather here, which is just the minimum of those two. All right, the last part of the model is for plate tectonics and the climate. So I'm parameterizing the fact that plate speed can depend on surface temperature based on some of my previous results where I did convection modeling and worked out some scaling laws for how this coupling works. It turns out I can parameterize it really simply with a simple linear function here, which matches the full convection scaling laws quite nicely for a pretty broad range of temperatures, the range of temperatures we're going to worry about here. And I'm using a very simple parameterization from the classic paper by Walker and others in 1981, and that's shown here. And the result of what that parameterization looks like is shown on the bottom here. And I want to point out quickly before moving on that even at these very high atmospheric CO2 levels, like 10 to 100 bars, with very high temperatures over 500 Kelvin, that's actually still within the liquid water stability field because the atmospheric pressure is so high. All right, so now we can solve these equations, model planetary evolution through time, coupled carbon cycle and plate tectonic model. I'm going to be very simple-minded. I'm going to keep all the parameters constant, actually, except for the plate speed, which I'm going to allow to vary with surface temperature. And that's because I want to isolate this coupling, this kind of complete coupling between climate and tectonics to see what happens. I'm going to pick a very conservative limit for the maximum erosion rate that's going to set the upper bound on the weathering due to this supply limitation. And that, basically what I did is just pick the largest erosion rates observed on Earth today, which are about 10,000 meters per million years. The fraction of subducted carbon that is degassed at arcs is going to be half. So half the carbon goes into the mantle, half comes out arcs. The fraction of upwelling mantle that degasses at ridges is calibrated to current day observations. I'm also assuming basically an Earth-sized, Earth-like planet. Total carbon inventory here comes from Sleep and Zonley, the range they use. And I'm using a modern day land fraction, at least for now, of 0.3. And finally, we can use Henry's law to maintain chemical equilibrium between the atmosphere and ocean. So that basically happens instantaneously on the scale of the model I'm looking at. All right, so here are the results. So I'm plotting the evolution of the mantle reservoir, plate reservoir, ocean reservoir, and atmosphere reservoir over time for 3 different initial conditions. So the 3 initial conditions are, the red line shows an initial condition where all the carbon initially is in the atmosphere and the ocean, and none of it is in the mantle. The other extreme end member, of course, would be all of the carbon initially in the mantle and none in the atmosphere and ocean. That's the green line. And then the blue line is in between, half the carbons initially in the atmosphere and ocean, half in the mantle. And the main point here is that, as you can see quite clearly, all of these initial conditions converge to the same steady state on something like a billion-year timescale, where that timescale ends up being controlled essentially by the plate velocity. So this already shows us really the answer to one of these questions I posed, and that's that the initial conditions actually don't matter. There's no real hysteresis here coming from initial CO2 levels. And the reason for that is actually fairly obvious almost in hindsight, and that's because it's just because the weathering feedback far outweighs the dependence of plate speed on surface temperature. So the weathering rate can vary by orders of magnitude as CO2 and temperature change. The plate speed ends up only varying by a factor of 2, which influences degassing. So the weathering feedback wins easily and can push everything to this same steady state. The other thing to point out here is that, so even though the plate speed dependence on surface temperature is very small and actually doesn't have much effect, in principle, it is actually more stabilizing and helps things erase the memory of initial conditions even more quickly. And that's because at warmer temperatures, when plates are slower, degassing is lower, in addition to the weathering rates being higher. All right, so now I'm going to move on to a different idea where I want to show you what it could take for a planet to actually lose these stabilizing weathering feedbacks of the carbon cycle. And to do that, I looked at the effect of small land fractions. So what I've done here is I've plotted the final steady state. So I'm kind of skipping the time-dependent evolution and just showing you the final state things reach as a function of changing the land fraction. So I'm plotting this. See, we've got atmospheric CO2 and surface temperature here. So if we start basically around today's Earth and just started dropping the land fraction, dropping the amount of land exposed, CO2 and surface temperature increase because when you decrease the amount of land, in principle, the weathering flux would go down. So you have to increase atmospheric CO2 to bring things back into balance with the degassing fluxes. So as you keep dropping the amount of land exposed, eventually you reach this critical point. So there's actually kind of a critical atmospheric CO2 level where the weathering flux will hit the supply limit and be capped, and it can't go up anymore. So that means we get essentially a runaway accumulation of CO2 in the atmosphere, and you have this huge jump in atmospheric CO2 and in surface temperatures. And this represents, like I just said, a switch between kinetically limited weathering to supply limited weathering. So this would mean that planets sitting in this regime, where the amount of land they have exposed allows weathering to be kinetically limited, will still be able to maintain these stabilizing climate feedbacks that help keep the planet basically habitable or able to have liquid water over longer time scales. Planets over here that get stuck in the supply limited weathering regime will be like this dashed line, where they won't be able to maintain these stabilizing climate feedbacks. And just the last point here before I wrap up is that, of course, so this maximum erosion rate I picked that sets the supply limit on weathering and the kind of cap on the weathering rate is fairly arbitrary. So, of course, we don't really know what that is. So if you vary that rate, and what I showed in the previous results is probably kind of a maximum that can reach. So if you vary that, then you can end up causing this transition to transport or supply limited weathering at larger land fractions. So I'm about out of time here, so I'll just skip to the conclusions. And I just want to acknowledge Josh West, Torsten Becker, Peter Driscoll, and John Chambers for their help. Thanks.
We have time for one quick question.
Yeah, I'm saying that ocean planets would have trouble keeping habitability over a longer time scale because they don't have a way to regulate their CO2. So the amount of CO2 would basically be kind of fixed. And What? What's that? Yeah, farther away in the habitable zone, it might be okay. That's right.
Thank you.